Woohoo! All right, so continuing on, we're now going to solve Laplace's equation in a different coordinate system. So we started by looking at a problem where the boundary conditions were squarish, right? We did that in class and we did that on the last video. And so it made sense to use Cartesian coordinates because they nicely match to our squarish boundary conditions. But sometimes we might have a boundary condition that is more spherical or cylindrical, right? These kinds of things pop up in nature a lot. So if we have boundary conditions that match another coordinate system better than they do Cartesian, it might make sense to do the work of solving Laplace's equation and matching the boundary conditions in that other coordinate system. So let's go through how we would do that in spherical coordinates. All right, so Laplace's equation is blah equal to 0. And we're going to separate variables just like we did in Cartesian coordinates. So you might already know the solution if you've taken quantum mechanics, right? Because when we're taking quantum, we have something that looks kind of like this, right? There's some constants in there. Let's just, who cares, right? And so this only depends on our radial part, and so that we know our solution to our Schrodinger's equation looks something like some radial part of our solution, which is going to be some complicated differential equation I have to solve, and some angular dependence. And we call these the spherical harmonics. Now, we're not going to talk about spherical harmonics in this class. They are the solution, the angular solution to Laplace's equation, right? Because just like this, when I divide the radial part out, I'm left with just the angular part equal to 0. So the same angular solution here is going to be the same here. The answer again is spherical coordinates. So I'm just trying to make connections to things that you already know. Now in quantum it really makes sense because you really care about that M. But in E and M, it's more about the procedure and getting an idea of it, plus we got a lot more to do. So what our textbook does is it says, all right, let's go ahead and make an assumption. Let's assume azimuthal symmetry. So d squared v d phi squared equals 0. So we're just saying that, you know, there's a sphere, right? And if I go around the angle phi in that sphere, right, that there's no change to the potential. So there's a symmetry there. I don't have to, and I already know what the solution's going to be. It's going to be spherical harmonics, and I could just start with that if I've already gone through those physics. But we're going to go through it step by step here so you can see how this builds up. This would be like one of the first steps in building up the spherical harmonics too. So it's not like we're not doing the same kind of physics. But we're going to go ahead and assume this. Now, we do this in physics in E&M 1. That's because that's what your textbook does. Now, if you were to pick out Jackson, which is the graduate E&M textbook, you would see that a lot of the problems they don't set that equal to 0, and they have some angular dependence in the phi direction. So you have to use the full-blown solution to Laplace's equation. Here we're going to find an easier version just to get started, get our feet wet to see what it's like, and then we'll move on. Okay, so if I go ahead and make the assumption that this is in fact true, that that's 0, then it's going to simplify this equation quite a bit. I'm going to have 1 over r squared ddr, r squared dv dr plus 1 over r squared sine theta dd theta sine theta dv d theta equals 0. So I'm going to go ahead and I'm going to multiply everything by r squared and clean it up a little bit. We're going to get the following equation. Cool. And then, just like before, I'm going to do my separation of variables. I'm going to say that there are two different functions. VR of theta is going to be equal to some function r of r and some function, I'm just going to go ahead and call it big theta as a function of theta. If we weren't going to have this to be this second derivative of the potential in the phi direction, that's symmetry, and to have that equal to 0, we would use y here for the spherical harmonics. Okay, I'm going to take this puppy here, and I'm going to plug it right into that differential equation. Okay, now here, this only depends on r and not theta. So I can pull out the theta term. And likewise, this term here only depends on theta. It doesn't depend on r, so out of the partial derivatives, I can pull the r function. Okay, I can divide this by, remember this whole thing is equal to 0. I can divide this by 1 over r theta, the whole darn thing, right? So when I divide it here by 0, of course 0 divided by some function is going to be 0. And if I do it here, we get 1 over r Okay, now, again, this is the magic that happens with the separation of variables. This part only depends on the parameter r. This part only depends on the parameter theta. And of course that's 0, right? So since this part only depends on r, and this part only depends on theta, if I put any value of r and theta into this, it doesn't matter, it should add up to 0. So that means that this part has to be a constant, and this part has to be a constant, right? Because no matter what I put in, I should get 0. Right? They have to cancel one another. So my initial instinct would be to say, oh, that's easy. You just put that as k and put that as minus k and you're done, right? But we have some hindsight as to what the differential equation will be, having done these problems a few times. So we're going to go ahead and choose a wacky constant to put in, but we're going to choose it because we know it's going to help us out later on. So we are going to choose that this is L plus 1, L times L plus 1, and this is minus L plus 1. And of course, that whole business adds up to 0, right? So I have two differential equations now I have to solve that only depend on one variable. This one only depends on r, and it'll give me capital R as a function. This one only depends on theta, and it'll give me capital theta as a function of little theta. Okay? So that's what we're going to do for the rest of this class. So let's dive in. Let's see, what my note solves the R equation first, so let's start with that. All right, so my R differential equation looks like 1 over big R, d dr, r squared, d big R, d little r, equals L times L plus 1. So the first thing I'm going to do is I'm just going to multiply both sides by the big R function. And that's going to give me okay, and I start shaking my head because this looks like a pain, right? I'm trying to think if I know of any function that is going to give me a solution like this off the top of my head. And I am thinking and I can't. So, crap. When you can't think of what the solution is going to be, you have a few choices. One thing you can do is you can solve it numerically, which many times I am a big fan of. But if you can get an analytical solution, it can be a good, huge, tremendous, wonderful thing to have. So what we're going to do is we're going to start by using the method of Frobenius. Woohoo! I'm a big fan of Frobenius, right? So we're just going to start by saying that R, as a solution, we're going to guess. Say that R is something like some constant A, R to the lambda. Right? I mean, it's just a guess. I don't know anything about lambda. I don't know anything about A. But I'm going to try them out. Okay, so I plug the crap in, right? So, right, this is a guess, yo. Right? And the only way we know if a guess works is if we try it out. Remember, with differential equations we can solve using any method as long as they work and they match the boundary conditions. All right, so we're going to take this bad puppy and we're going to put it right in there. So, and if it solves a differential equation, in fact, we are in business. A, R to the lambda equals L plus 1, A, R to the lambda. Well, the A is a constant, so it's the A is on this side of the equation, A is on that side of the equation. The A goes bye-bye. All right, so good. We're already getting this nicely set up. That A, that constant, looks like it's going to be working, right? All right, now what about the R to the lambda? Well, we have some calculus to do. So this is d dr, r squared. Now if I take the derivative of r to the lambda, it's going to be lambda, right, r to the lambda minus 1. Right, because by taking the derivative of this, I take the power down, and I just subtract 1 from that. And of course, this is going to be equal to L plus 1, r to the lambda. Okay, so I can pull the lambda out, pull it out of the differential equation. It's a constant, right? And then I have r squared times r to the lambda minus 1. So I got to do some algebra. Right? We're going to add the exponents. Lambda plus 1. Right? R to the lambda minus 1 times r squared means I add 2 to the exponent. So minus 1 plus 2 becomes plus 1. Now I take the derivative of this. Well, just like before, I'm going to take the power, drop it down, and I'm going to subtract 1 from it. So I get lambda plus 1, r to the lambda equals L plus 1, r to the lambda. Holy cow! The r to the lambdas cancel out. Oh, yes. Now, you'll remember from Math Method 2, if you've taken it, that this can sometimes be a pain in the butt when you use method of Frobenius, because sometimes you actually have to look at this as like a series, right? And you got to think about the series solutions, and that can be trouble. And you have to think about how all the A's are interconnected. Not here, though. Here, they nicely go away. Okay, so we're left with, this is a solution provided the following, that lambda times lambda plus 1 equals L plus 1. Pretty cool, huh? So at first you say, oh my gosh, that's easy. When L equals lambda, we got a solution. Yeah, right? No crap. So, but we can dive in a little bit deeper to this by completing the square. Let's solve for the roots. So we have lambda squared plus lambda equals L squared plus L. And I'm going to complete the square on this side of the equation by adding the following term, plus 1/4 to it, right? And I'm going to go ahead and do, if I do plus 1/4 on this side of the equation, I have to do plus 1/4 on that side of the equation. But the good thing about this is that this is exactly the terms that I need to complete the square in this equation. So this becomes lambda plus 1/2 squared. And this becomes L plus 1/2 squared. Now I'm going to do something wacky. I'm going to take the square root of both sides of the equation and solve for lambda. All right, so when I do that, when I take the square root of this, there's going to be two roots, right? There's going to be the positive root, and there's going to be the negative root. So this is going to be plus or minus L plus 1/2. Okay, so I can solve. Lambda is equal to plus or minus L. And if I bring this over here, it could be a negative plus or minus L plus or minus 1/2 minus 1/2. All right, so there's two choices, right? There is lambda equals plus L plus 1/2 minus 1/2, or L. Or, we'll call this the plus one, there's lambda minus, which is the negative root, minus L minus 1/2 minus 1/2 is minus L minus 1. So here's the great thing. It's like unbelievably, I can't believe it's not butter, amazingly fantastic solution. We try with one solution, and look, we get two roots. This is a second order differential equation. And if I have a second order differential equation, I know I should have two constants, right? Two separate solutions. And so here, I get for free those solutions. I get one where L is equal to lambda, and I get another where L minus is equal to minus L minus 1. So the R, as a function of our solution, is going to be AL R to the L plus BL times 1 over R to the L plus 1. And this function uniquely defines this. This solution is the solution to this differential equation. Now let's look at the theta part, right? d theta, theta, sine of theta, d capital theta, d theta, and then there's a big 1 over big theta here. And this is going to be equal to minus L plus 1, sine theta. Right? Sorry, as I had it in my notes before, there was a sine theta here. And kind of the first step that we do is we kind of get these things out of the denominator here and push them on over. We get d theta sine theta, d big theta, d little theta, equals minus L plus 1, sine theta, big theta. All right, so what do we do here with this function now? Well, now we do something that's extra wacky. We look at this and we say, well crap, that's terrible. Like, I don't know how to solve that. Now, one solution would be use the method of Frobenius, right? And let me be frank. If I were doing this as an experimental physicist, I would look and stare at the thing for like a day. I might try the method of Frobenius. I might try to see if there was some like solution I could think of. But then I would, of course, Google search it. But then I'd probably give up because, you know, things like that are pretty scary, and I'd do it numerically. But it turns out that this one is one that if you look up, you'll find this is actually a specific differential equation that pops up a lot in physics. So much so that we've worked out all the analytical solutions for it, and we nicely know that this is the Legendre differential equation. Okay, I always have to. So, what do we do when we want to solve the Legendre differential equation? Well, there's a bunch of things. So the first thing that we have to do is we have to make a conversion, right? The conversion we're going to make is we are going to change from theta to x. So we're going to start by saying that x is equal to the cosine of theta. And dx is going to be equal to, well, the derivative of cosine is minus sine theta times d theta. Okay, so what does that mean? Well, if I divide through here by theta, we have d sine theta d theta. Well, I know that sine theta d theta is just going to be minus d dx. Right? Okay. Then I look at this and I say, well, crap, I have a sine theta here, and now I have my the solution I'm looking for, dd big theta, and now what I'm going to do is I'm going to plug in for dd theta, and that's going to be a minus dx over the sine of theta. Right? So at first you think, well, shit, now I'm screwed. Now I got a theta in there, but it works out. It's one of those wacky ones that works out. So if you look, you take the sine theta up, right? Because it's on the denominator and the denominator. So you get sine squared theta d phi dx equals minus L plus 1 big theta. Okay, so we still have to get it in terms of x, and there's still some theta dependence. So how can I do that? Well, I know that x is equal to the cosine of x, So if that's true, and I take the cosine squared theta plus the sine squared theta, I know with that identity that's going to add up to 1. Or x squared plus sine squared theta equals 1. So if I know that, then I know that sine squared theta is just going to be 1 minus x squared. The minus signs cancel here, sorry. So I'm left with d dx 1 minus x squared, right? D theta dx equals minus L plus 1. Okay? All right, so if I want to simplify this even further, what I can do is use the product rule. When I take this derivative on here, I'm going to take the derivative of this term, and then I'm going to take the derivative of that term. So you get the derivative of this term becomes minus 2 dx d phi dx. And if I take the derivative of this and hold that constant, it's going to be 1 minus x squared d phi squared dx squared. And of course that's going to be equal to minus L plus 1 times big theta. Okay, now we can rearrange some. So we get 1 minus x squared d phi dx squared minus 2x d phi dx plus L plus 1 big theta equals 0. Okay? This has the solution of the Legendre polynomials. So let's talk about them, and then we'll make another video for how we get that solution. So I always get all the constants wrong, that's why I gotta look it up. So the solution to this equation is P, right? So P of x is equal to 1 over 2 factorial, sorry, 1 over 2 to the L power, L factorial, the Lth derivative of x times x squared minus 1 to the Lth power. And the solution, right, is going to be PL cosine theta, right? So if I plug this in for x, that is a valid solution to that differential equation, right? So if I take this here, remember that I'm doing this not for x, which I don't really know about, I'm doing it for the cosine of theta. Okay, so let's take a look at